The Multimedia IP DMA verification platform. Abstract. DMA verification is usually done by a senior verification engineer because even a single bus protocol violation could hang out with the whole SoC. In this paper, we introduced a DMA verification platform for multimedia IP that could be easily used by the verification designers and could accumulate DMA verification knowledge of experienced engineers without much effort. Though through these platforms, even a novice verification engineer could develop a new DMA test bench in 30 minutes, and we could verify the several DMA instances at the same time with sufficient verification quality. Introduction. In recent SoC and Exynos SoC, most multimedia IP require direct external memory access to process a large amount of image or voice data. For this reason, the multimedia IPs have several DMA instances to read or write various types of data. Some examples can be an image scaler, which directly reads images from and write to DRAM through the bus. If the DMA instance has a bus system could be hanged, and this could affect the whole SoC. Therefore, DMA should be verified very carefully to obtain a satisfactory verification quality. So one senior verification engineer could normally only verify up to 2 or 3 DMA instances at the same time. However, in recent years, the numbers of DMAs in multimedia IPs for Exynos SoC are increasing to meet the market's needs for the processing power, and it's become increasingly difficult to meet the verification schedule where the number of senior verification engineers are limited. In order to overcome this situation, we create a multimedia IP DMA verification platform that could be easily used by the verification beginners and could accumulate DMA verification knowledge of experienced engineers to this platform. So far, this verification platform has undergone the several factoring the processes for more engineers to this platform. So far is for more convenience use. Currently, the platform is well established in our team and make it possible to perform several DMA verification projects successfully with less manpower. This paper, we will describe what the multimedia IP DMA verification platform, hereafter we call it MDVP, is that its development process of the MDVP, including why and how it was developed. The background. Unlike general purpose DMA for CPU, multimedia IP DMA of Exynos SoC has a single structure and is included in the multimedia IP as shown in Figure 1. Figure 1 is the architecture of general multimedia IP that has a bus interface. However, multimedia IP DMAs have various types as they have to support different types of data format and interface protocol between DMA and the processing engine. As a result, many DMA instances for multimedia IPs are verified in one SoC project, and every DMA instance has some common items that should be checked. 1. Check the RTL output is matched to the expected value. Check if the protocol of on-the-fly interface is correct. Check if there is or bus requests are expected. 4. And check AXI protocol. Among the 4 items above, item 3 and 4 are related to the bus, and therefore to thoroughly check those items, verification engineers should be an expert in the entire system. This makes novice engineers hard to conduct DMA verification without any help. Hence, in the past, mainly senior verification engineer verified multimedia IP DMA. and the senior engineer made a new test bench by utilizing the test bench of the previous project as much as possible to perform the new DMA verification. So because the given time was not enough, the senior verification engineer had to perform the following tasks in the process of creating a new DMA test bench. 1. Check the differences between the specification of a new DMA and the previous test bench. 2. Modification or implementation of driver and monitor according to the specification of on-the-fly interface. 3. Maintenance of DMA reference model if necessary. 4. Maintenance of the scoreboard to match output with golden value if necessary. 5 is generation of compressed DMA, FDMA supported data compressor. Maintenance of VIPs such as valid bus transition checker and AXI slave memory model. 7. Maintenance of regression violation environment. So in addition, the senior verification engineer had to continue to help the junior or novice verification engineers directly and indirectly by conducting code review on the existing test bench or sharing the developed VIPs to get the satisfactory verification quality of DMA verification. For this reason, even though the senior verification engineer could verify more, senior verification engineer in one SOC project generally verified on only 2 or 3 DMA instances. Recently, as the function of the multimedia IPs has greatly expanded, the development of a DMA instance has also increased dramatically. So, however, the number of senior verification engineers are limited, and therefore the DMA development has become a critical path in the whole multimedia IP development. To overcome this situation, we devised the MDVP for 4 reasons. 1. Test bench was required to get up enough verification quality, even if the novice verification engineer do the job. So this ensure the test bench that can work well was necessary to the release in a short time. 3. We wanted to maximize the amount of codes being reused. 4. And we also wanted to provide an environment that can rapidly ramp up novice verification engineer. So we will describe the detail of MDVP at the next chapter. 3 is what is MDVP? MDVP is an UVM-based verification platform specialized for multimedia IP DMA. MDVP consists of a DMA reference model for a multimedia IP DMA, a reusable test bench that can be shared among different DMA instances, and a configurable UVM test bench according to the specification of a DMA instance. A. Input data for multimedia IP DMA, and generally the behavior of the multimedia IP DMA does not vary depending on the patterns of data to write or read. So random data are normally used as input data. However, in case of DMA including the data compressor to reduce the bandwidth or memory footprint, random data input may not be sufficient. Therefore, MDVP provides random data pattern and non-random data pattern, for example image, as input of DMA, in particular in the case of the DMA for image processing. We use image magic software to generate various natural data patterns that desire image resolution, so pixel bit with an image format such as Bayer, RGB, and YUV, so based on the tens of thousands predefined imaging dB. Reference model for MDVP. Reference model for a multimedia IP had its own DMA model, but it was not suitable for use for the DMA reference model in the MDVP because the IP DMA model was implemented as various forms and it took a lot of time to convert the IP DMA model to the DMA reference model for MDVP. So we developed a newly DMA reference model for the MDVP that supports all kinds of memory format for multimedia IP DMA in Exynos associated through analyzing every IP DMA model. The main roles of a DMA reference model are the pixel formatting and converting memory map using input data pattern and the configuration of DMA such as base address, stride, pixel format, and memory format. The output of the DMA reference model of MDVP consists of two types of information as below. The one is valid address information. They are used for a valid bus transaction checker, and two, expected value. They are used as input their RDBMA and reference data for WDMA. So in MDVP, the valid address and expected value information is stored the inform in figure 2. We call it as info underscore q and data underscore q. And since the info underscore q is created only once in DMA sequences, there is an advantage, and the UVC and the VIPs do not need to recalculate valid addresses. So figure 2 is an example of info under Q and data Q. And C, reusable test bench. Most of the multimedia IP DMA have a similar structure. In this case, the majority of the test bench can be reused by the using on-duty wrapper and instances DMA as shown in figure 3. Therefore, the verification engineer does not need to spend time to debug, and they can proceed with faster and more effective verification. Figure 3. The architecture of reusable test bench of MDVP. Reusable test bench consists of a bus functional model for ABP, clock and reset generator, valid bus transition checker, and AXI slave memory model. Among them, valid bus transaction checker and AXI slave model will be described in detail below. 1. Valid bus transition checker in MDVP. We define the role of a scoreboard for WDMA verification as checking whether there is expected value in the expected address after finishing DMA operation. However, if the DMA issues an unintended write bus transaction to access the invalid address region, so the scoreboard cannot detect this. And in the case of RDMA, scoreboard for output of on-the-fly interface cannot detect unintended read-bus and transactions of external memory. If the unintended read data is not used as output, so this unintended bus request should be detected in somewhere, because the request can affect performance degradation of the DMA, and the MDVP and valid bus transaction checkers uses valid address information of DMA, so which is made by the DMA reference model as input, and a checker can detect unintended bus request by checking an address whenever a bus request occurs. 2. The AXI slave memory models. The most EDA vendors provide AXI slave memory models in VIP form, and many verification engineers are using the VIP to conduct DMA or bus verification. In the case of the multimedia IP DMA verification, however, we often use only a part of the VIP function provided by EDA vendor. So we have developed the in-house AXI slave memory model that is optimized for multimedia API IP DMA verification by integrating in-house AXI slave model. We were able to increase simulation speed by 100% compared to the test bench using a commercial VIP, and it had a great influence on integration turnaround time reduction. Moreover, we were able to reduce the VIP license cost as well. The configurable UVM test bench. The main differences among multimedia IP DMA instances are types of on-the-fly interfaces connected to the processing engine and the formats of data written to or read from the external memory. In order to verify the DMA instances that have differences with the test bench, driver, monitor, and checker, and scoreboard are required for the each on-the-fly interface and memory format converter, which can express various memory formats, is also needed. Therefore, the configurable UVM test bench of MDVP provide various UVCs corresponding to the fly interface and provides an also UVM test bench skeleton script consisting of various pre-implemented sequences and a method that is input data generator, DMA reference model, UVC link method, and a common DMA operation sequence so that the new DMA test bench can be released quickly. And MDVP, even the novice engineers and novice verification engineers do. So figure 4 it shows the architecture of configurable UVM test bench in MDVP. So this is a figure 4, the architecture of the configurable UVM test bench of MDVP. This configurable UVM test bench has undergone several refactoring processes over several projects. The earliest configurable UVM test bench was developed on focusing the usability of implemented UVCs. Below describe how to create a reusable UVC and how to conveniently use it in multimedia IP DMA verification. 1. DMA agent. MDVP provides a DMA agent to which a driver, monitor, checker, and a scoreboard were connected to with UVM_analysis_ port. When the development of the UVC for the new on-the-fly interface was required, and the DMA agent can help engineers to focus only on a component implementation regardless of the test bench architecture. As 2. DMA-based test. MDVP provides the guidance to wave factory overriding for UVC. In multimedia IP DMA verification, the configuration of UVC does not need to change dynamically on the simulation runtime. So each DMA verification engineer can configure the desired DMA verification environment simply through the factory overriding the UVC required for DMA verification in DMA IP in the DMA_IP_base_test class, and all test scenario classes inherited DMA-based test, so redundant code for UVC configuration could be reduced. 3. Parameterized component and interface. Multimedia IP DMA uses various types on the fly. The interfaces and these interfaces may have the same type, but can differ only in a bit of width of signal. Therefore, we implemented interfaces in UVC using the parameter of the bit width of the signal as shown in figure 5. The figure 5 is the example of code for parameterized interface in a component. So by using the above technique, the DMA verification team consisting one senior engineer, 2 junior engineers, and 2 novice verification engineers carried out the first project of verifying 25 DMA instances at the same time. So at the beginning of the verification, it took a lot of time to develop the UVC libraries for the interfaces. But once the UVC were ready, the time for test benching implementation gradually decreased. However, Despite the reuse of UVCs, test bench bug occurred frequently because each verification engineer still had to implement its own DMA_V sequence in accordance with the DMA instance. By this region, we considered MDVP with the reusable sequences and test codes for all DMA verifications. As a result, we built a newly defined base_V sequence and a defined DMA_V sequence in MDVP to minimize code development. Figure 6 is the architecture of a common test and sequence of MDVP. 1. Base_V sequence. We found the common test scenarios used for each DMA verification while performing the first project with the MDVP and created an additional sequence layer named base_V sequence. The common test scenarios were built into base_V sequence with control nodes as random variables. The control nodes were determined in each common test scenarios. The common test scenarios could activate control nodes by the factory-overridden base_V sequence, with the scenario sequence having desired control node in common test scenarios as figure 6. So as a result, each verification engineer can minimize code development about the test scenario. 2. DMA_V sequence. In earliest MDVP, verification engineer had to develop their own DMA_V sequence and had a lot of time to build the sequence. Therefore, we redefined and improved this sequence for more efficient test bench development. In the revised MDVP, the DMA_V sequence has a sequence of function tasks that can be used for every DMA verification. This sequence consists of a predefined method that are commonly used for all the DMA verification and the empty method that need to be developed differently for each DMA verification. Thus, a verification engineer can complete the DMA_IP_ sequence quickly by inheriting the DMA_V sequence and just developing empty method according to the DMA specification. 3. Parameterized sequence. For parameterized UVCs, both interface and sequence item had to be implemented using parameters. In the early stage of MDVP, however, the parameters were not well defined in the DMA_IP_ sequence, so that the verification engineer had to develop a large number of code for a connection between the configuration sequence and a sequence item for a UVC. In addition, on a number of test bench, both underscoring the process and novice verification engineer was difficult to link the configuration sequence to sequence item for UVC, for each UVC. Therefore, we create the parameterized DMA_V sequence according to the on-the-fly interface parameter, and we also built in method for linking configuration sequence and the sequence item of UVC in MDVP. These methods are developed by the parameterized subroutines because the virtuals and task function cannot support method overloading with other argument. The conclusion: the MDVP is designed to verify the multimedia IP's DMA instances efficiently with less manpower, and it had used on several DMA verification projects for Exynos SoC. At the first project using MDVP, it took a day to release initial test bench that worked as well before. So, however, the newly developed UVCs and the sequence accumulated in the MDVP after undergoing the several projects. It now takes only three It now takes only 30 minutes for a novice engineer to build a new test bench for a new DMA verification, and also DMA verification team consists of 5 engineers can handle more than 20 DVMA verifications successfully in a given schedule. Table 1 summarizes the effect of applying the MDVP to the DMA verification. Table 1 is the effect of applying the MDVP. Oh, right. Okay. Thank you. Today, I read this paper, Multimedia IP DMA Verification Platform. Thank you for your time and see you next time.